regions of the field.
Oh, sorry, that's not the beginning. Speaking at the beginning. Can you hear me okay?
Yes.
Okay. So I'm Craig Schwartz, and I work at Berkeley in SLAC. I specifically want to begin this talk by sort of offering an apology. So I wrote an abstract that was far too broad, and then I thought about really narrowing it down and giving really detailed information on one thing, but instead I'm going to give a talk on three things, and I'm sort of not going to give all the details. So for that reason, I want to point out that my email address is here if you have any questions, and besides that, I will be around all week, and you have full permission to come harass me with it, whatever you want. So be aware there's going to be things that aren't well explained, and I know that. All right, so this talk is going to cover three basic things. We're going to talk about using what's called vibration rotation tunneling spectroscopy. And we're going to use that to solve specifically the small water clusters from about 2 to 8 water molecules. We're also going to show some dynamics there. Then we're going to pivot and we're going to start working with some X-ray spectroscopy. And we're going to show you you've heard a lot already about how people have been talking about how things can structure water. Well, we're going to take it to its sort of logical extreme, and we're going to drive a phase transition. So we're going to show you that square ice is actually a new phase of water, stable at room temperature when it's found in graphene. Finally, I'm going to introduce to you a new form of surface spectroscopy, and it's got a high sensitivity, which I'm going to show. And I'm going to finally use that to sort of offer an opportunity, if you want to come work with us, as we're hopefully going to solve the liquid water service in the next year or two. So, most of the talks that we've heard have been here in the near IR, and you've seen all sorts of really cool results you can get, but as has been pointed out, you don't get the whole picture. So there's some really cool stuff that you can get out here in the far infrared, roughly 1/1000th the energy of room lights, and there's also some really cool stuff you can get out here in the X-ray, roughly 1,000 times the energy of room lights. And so this gives you sort of different and complementary information. All right, so how do you do, or what is vibration rotation tunneling spectroscopy? So vibration rotation tunneling spectroscopy is basically high resolution far infrared spectroscopy. But it's actually really hard to do. I don't know if many people here work in the terahertz, but generating really sharp lines in the terahertz is an enormous nightmare. You can't just buy a spectrometer that you can put on your desk and get high enough resolution to see sharp lines like this. You have to go through an incredible amount of effort and either mix a CO2 or quantum cascade laser with some microwaves, with a diode they no longer make, such that the only group in the world still doing this is Rich Sakeley's group, and that's only because they don't make the diodes and no one can afford the hundreds of thousands of dollars to get them to remake it. So when those diodes die, this experiment may be done forever. We'll have to wait and see. And so you combine this really high resolution spectrometer, which you can tune, with a cluster source. In this case I showed methanol because that's the slide that Will gave me. But basically you just pass water, or some helium over water, or in this case methanol, and you create a supersonic expansion, and you can get a cluster. And doing that, you can get really, really nice sharp lines, and that's really important because it describes these low energy vibration rotation tunneling interactions. So right here we have the water tetramer, and as you can see, it's 4 oxygens in a plane, and then there's 4 hydrogen bonds going up, down, and you can use a photon of the right frequency to drive a specific transition from up, down, to down, up, as I show over there. And what's really nice about this is because the lines are so sharp, you can build really accurate Hamiltonians, and you can build really accurate models for these small molecules. And I think the best success of this, actually, is probably the water dimer. So this is the big first paper that came out maybe 30 years ago. They showed that the water dimer is about 3 angstroms between oxygens. You can get all these bond distances and angles with really high precision, and particularly they can do that because there's 6 intramolecular modes in the water dimer, and now they've all been measured. So this is a problem that has been basically destroyed. We've put everything we can at it. The bond strength is 3.4 kcals per mole, and you can even see in certain cases where you can know exactly what's happening by isotopic substitution. In the case of this is the in-plane bend, or shown there also, you can drive it so the donor becomes the acceptor. And you can do all this with only a fraction of the energy of room temperature. Now, I think the dimer is a pretty interesting case, but to me, actually, the really interesting case is to start with the Pentamer. And the reason the Pentamer is so interesting is 2 reasons. First off, it's the first 3D structure, so everything else through the tetramer, all the oxygens are in the plane. When you finally get to the Pentamer, you get this sort of slight puckering. And with a very small amount of energy, again, we're talking about, 1/1000th room lights, you can drive a structural transition. So this is you're lowering the symmetry. But I think the coolest example is actually this one here, where you can actually make the structure more 3D. You can drive that oxygen farther out of the plane just with really small amounts of energy. And finally, Will, who's the only person still doing this, wanted me to point out his latest big victory, which was demonstrating the Octamer. So the Octamer is as large as we've ever gotten. This is 8 water molecules, but it also sort of indicates the sort of downside of this technique. So this technique is really powerful, but even by the time you're getting up to 8 water molecules, at experimental temperatures, which is roughly room temperature, you're getting, it's a bit colder, but it's in the ballpark, you're already getting 2 structures that are present. So as you get to more and more water molecules and bigger, it's not going to be possible to keep doing this. So the bulk water structure looks something like that. And that's just not the kind of thing where these sort of sharp lines and building custom Hamiltonians is going to work. So this is a really cool technique for understanding really small clusters. But it cannot and will not get you all the way to bulk water. So for that reason, we're going to pivot, and I'm going to talk about what I do mostly now, which is X-ray spectroscopy. And if there's anybody out here who does X-ray spectroscopy, I'm going to also lump it in with electron energy loss spectroscopy. I know that's wrong, but for the purpose of this talk, it's good enough. So X-ray spectroscopy, rather than happening at, say, 100 wave numbers, we're going to have it at hundreds of eV. So in the case of this is an isolated water molecule, if you put enough energy, you're going to excite from the core orbitals, which I guess you guys probably can't see that well, but it's the 1s's of the oxygen. And you excite into these higher lying antibonding states, like the 4A1 and the 2B2. And the reason you go through the effort of doing this, because it involves big machines and it costs a lot of money, is that it gives you access to information you otherwise couldn't get, because these are really sensitive orbitals, they're really big, so it's really sensitive to the environment. And the other advantage is that oxygen is really well separated from carbon and from nitrogen. So you have an elemental probe, which is also nice. All right, I need to introduce one material which isn't water, and that's graphene or graphite. So graphite, when you get a single layer of it, it's graphene. It's the 6 carbon cycle you see there. It's got all sorts of cool physics properties for those of you who are physicists. It's a perfect thermal conductor. Its Fermi energy meets at a single point called the Dirac point. It was awarded the Nobel Prize in Physics a couple years ago, the discovery of it. But for the purpose of this talk, the most important thing is that it's really strong. In fact, it's the strongest material known per weight. All right, and so this is a paper that came out a couple years ago now from a group in Germany and some people in China and England. And what they did was they grew some CVD, or by CVD they grew graphene, and then they put a water drop on top of it, and they put a graphene top, they put another sheet of graphene on it. So you got a graphene water, graphene sandwich. And then they left it overnight. They came back the next day, and for the most part, you saw nothing. You would usually just see bilayer graphene. But sometimes you would see something weird, and that's what's shown here. And you're probably thinking, that looks square, and so this red box is blown up over here. And it actually is square, you're not wrong. If you do an autocorrelation, or equivalently, they also did diffraction on it, you can see the 4 points there. That's the water. And actually, if you look closely, you can see these guys, which correspond to the graphene in the hexagon. I don't know if you guys can see that. It's a bit weak. Now, the other thing is that as they would make these measurements, and they were doing TEM, so it takes a couple of seconds to make a measurement. You make a measurement, you wait a couple of seconds, you repeat. They would see some things move around. So they have to explain this result. Also, I want to point out that the distance between those dots is 2.81 angstroms, which is roughly equivalent to what you would see in liquid water. So it's convincingly, or I think convincingly, water, but explaining this is challenging. And so what they did next, and I don't know if anybody here does TEM, but there is a standard way to determine the thickness of something by TEM. You take a sample and you rotate it. The problem is that in this particular case, when you rotate the sample, it moves, so you can't actually get the thickness that way. So they had to go to a relatively heroic task, and that is that they took this and they said, here's a really high resolution spectrum, or high resolution image, and they said, these dots are way sharper than here, and then they did some theory behind it, and they said, this corresponds to water stacking on top of water, so you have a multi-layer sample, and not just you have a multi-layer sample, but you have a multi-layer sample with what's called AA stacked. So you have a water, an oxygen on top of an oxygen. Specifically, that has to be true, is what they're saying, in order to get this. I'm going to point out again that this is not a standard technique, and I'll show you why as we go forward. They also did EELs, which I want you to think of as an X-ray spectrum. And what they basically showed was here is the spectrum in the ice region, so where there was all those squares. And they said, look, this looks different than where there's no squares. That's this reference region, which they said basically nothing's there. So all they wanted to show is that it contains a lot of oxygen, therefore it's water. And now they have to explain this, right? You're publishing in a prestigious journal, you're expected to do that. Now, if you were going to simulate this, I'm guessing all of you would just take graphene, take water, take graphene, and just run a simulation. The problem is if you do that, you don't get the right result. You get basically a drop of liquid water and graphene. So they went to pretty heroic lengths to try to reproduce this. They built this pretty elaborate setup with water on the outside and a slit that they could control the thickness of graphene, and then they would apply tremendous, and I'm talking gigapascals of pressure, to drive it inward. And if you do this with a monolayer, you get basically a square structure. I think that's a pretty good fit. If you do it with a multilayer, though, so basically if you make the slit thicker, you can get up to bilayers and trilayers, they said, you get a multilayer, but it's not AA stacked. So I'd say I have two problems with this. Number one, this does not agree with their result. And number two, and I think more significantly, it's not obvious that this actually ties into their experiment. I mean, it's conceptually a bit different. So my boss at the time, David Prendergast, threw this on my desk and said, figure it out. And I said, okay. And so I want to start again with, here's their spectrum. It's this black guy here. That's a square ice experiment. The peak corresponds to about 540 eV. So what I did was that experiment I just talked about in a computer. You put graphene, water, graphene, and you get a liquid water droplet. And what you see is that you get a peak too low in energy. All right, and I want to point out that we're making this simulation in two different ways. So you can measure this, you can imagine two different ways. You can measure it, graphene, water, graphene, going through the sample. And that's actually how they measured it, because that's easy. You just go straight through the sample. You could also do it in grazing incidence. So you could come perpendicular and basically not touch the graphene and go straight through the sample. They didn't do that, but I'm showing that as an example so you can kind of get an idea of what's going on here. The important thing to realize is that this is so strong because it corresponds to OH bonds pointing in the direction of the electron travel. So if you have graphene, water, graphene as they measured it, if the OH bond points towards the graphene at all, you're going to see a peak at lower energy. Then you can verify this as we did right here. So we're going to take that spectrum they had earlier, or that proposal structure they had earlier, and you can do these calculations, and you can show that this right here, you get basically a match when you go through the sample. So if the electrons are coming out of the board here, then you would get basically the right spectrum. This peak right here is an artifact in box size, it's not real. And if you come parallel to the sample, you see this enormous low energy peak, all due to those OH bonds interacting. Now this has specific implications that are perhaps not obvious yet. It means that OH bonds you can't have an OHO bond, right? You can't have a hydrogen bond. Because if you do, then there would be oxygens or hydrogens pointed at the graphene. And so it actually becomes possible to now do a structure search. So what we have here is an energy diagram. So this is 0, 0 is when oxygens are on top of each other, or 0, 2.81, or 2.81, 2.81. Basically, where there's a peak, there should be a value. So what they ended up seeing, so what you see here is the opposite of what they're claiming. What we have here is evidence that it can't AA stack because the energetics aren't there. So this actually causes another problem. Now we're saying you can't have OHs pointing at each other, and if they're OO stacked, if they're AA stacked, it doesn't work. So this means you now have no multilayers. So how do we explain the contrast difference? All right, next problem. So I showed you that reference spectrum earlier, right? That's this black line, I blew it up. There's a really good fit here with this dashed line. That dashed line is the literature spectrum for graphene oxide. The reason that they were having such a hard time making this sample and making it over and over again is that in order to make it work, you actually needed to make a sample that wasn't very good. So the better you did, in other words, the more you suffered. And we showed that, and this is not particularly convincing, but we did show that it's consistent with things like epoxides or hydroxyls that could be in graphene oxide. The exact identity of that is not hugely important. The importance is that there's something defective there. Now, why does this matter? All right, so as you can imagine, this thing is going to, square ice would normally just move. There's nothing keeping it pinned. And in order to make a TEM measurement, things need to be stable on the time scale of seconds. So what you can do is you can drop a single defect into graphene. And if you do that, you get basically a pinwheel. So your water is going to spin around it, and it doesn't stay still. If you add a second defect into your graphene, and you have 2 hydrogens, you actually get nice. And then your stability varies depending basically on how well it's stuck. So the contrast difference they were seeing is due primarily not to multi-layers, but rather due to these binding functions. All right, and so as I mentioned earlier, what you want to be able to do is just do a simulation. I'm going to show that here. This is just graphene, water, graphene. And we're going to do what's called metadynamics to speed this up, but otherwise it's a standard MD simulation. And we're going to drive this, and you're going to start seeing these things squaring up, and then it's going to basically wipe all at once. And it should start to, yeah, you can start seeing it happening in there. And so what's driving this is this really strong pressure from the graphene sheets, and here it's going to go all at once. And I want to point out that this is stable, and I don't mean like stable in that like it's kind of stable. Like this is the thermodynamically stable state of the system. It should stay this way, we think, until basically the end of the universe. So, and you can do a bunch of math, which I can't detail here, and you can show that you can make clusters of about 1,000 water molecules at room temperature, and you can actually keep adding defects to ways to cheat to get bigger and bigger clusters of this. And it should form spontaneously. So as the water's evaporating, you're actually going to make this happen automatically. And you can see here that the delta G is negative, although there is a big transition state. And the main reason I wanted to point this out actually is because of this figure right here. But we're going to get there in a second. So first, the total pressure actually doesn't change that much over the course of that simulation. What does change is the directionality of the pressure. So the XY pressure goes from about 1.8 to about 2 gigapascals. And your Z pressure, so your pressure perpendicular, drops from about 0.8 gigapascals to about 0.3 gigapascals. And that's actually what drives this phase transition. Finally, it should be spectrally distinct in the near IR. So I made a really half-hearted attempt to measure this, where I took graphene, took water, took graphene, and put it in a near IR spectrometer. That's not good enough. You should do better than me. But there are ways you can do that by doing things like tip result measurements. So if somebody wants to go out there and measure it, it should be unique. And that's a measurement that can be gotten. All right, with that, I'm going to change. I'm going to change one last time to talk about maybe another big outstanding problem in water, and that is the water surface. So the standard way to measure surface, maybe not the standard, one of the most common ways to measure surfaces is to use something called sum frequency generation or second harmonic generation using nonlinear optics. And the way this particular nonlinear optic works is that you add 2 photons of identical energy. So say 1 EV and 1 EV, and you get out photons of, say, 2 EV. Now, you're probably already thinking, but Craig, 1 plus 1 is 2 is pretty linear, and that's true. But it's actually nonlinear with respect to the electric field. And the reason that people go through this effort of doing this technique is that it's surface specific under the dipole approximation. So it's a way to actually look specifically at surfaces. And there's a whole literature about this, and I chose this one more or less at random. But here they show the thiocyanate and how it binds at different temperatures to the water surface. There's also all sorts of papers on things like polymers binding to water surfaces and proteins binding to water surfaces, and pretty much anything you can imagine you can look at with this. They also do things like buried interfaces, like water on mica, things like that. So it's a really powerful technique, but they're doing this typically in the visible, and so you sort of lack the sensitivity of X-rays. Now, this was actually first demonstrated 4 years ago down the road at SACLA. They did this, but they did it at a really high energy. They did it at 7,300 electron volts, or the wavelength of light is 1.7 angstroms. And at this wavelength, it's actually not a surface-sensitive probe. So there's 3 different ways you can think about it, depending on who you're talking to. If you're talking to a bunch of plasma physicists, you tell them that it's so far above the binding energy of the carbon that it doesn't behave like a balanced system. It's basically a plasma. If you are talking to a bunch of chemists, you say, oh, the wavelength is 1.7 angstroms. The spacing between the atoms is order of 1.7 angstroms. In essence, everything is a surface. So it's kind of a surface probe if everything's a surface. And the final way to think about this is if you're a solid-state physicist, the Brillouin zone is different. One important thing that makes this technique basically hopeless to be useful is the efficiency is 10 to the minus 11. That probably doesn't mean a lot to you guys, but at an efficiency that low, you start having problems with with you're going to damage every sample. And that's because there's a certain energy that it takes to bind an electron to a proton. And at these sorts of efficiencies, the fields required are above that, and you will inevitably damage every sample you take. So it is a massively expensive and difficult experiment. But we wanted to get around that. So we wanted to do soft X-rays, and soft X-rays had a lot of advantages. In particular, so here in black is the linear spectrum for graphite, and you'll notice that there's all sorts of information there. And we're going to take it at 3 energies, at 260 eV, 284 eV, and 308 eV. And what we're going to do is we're going to pass through 2 photons, either at a variety of energies, ranging from 260 to 308, and we're going to get back out photons at twice that energy. Now, what we're going to do here is we're just going to generate a curve, and we're going to do it for different sample thicknesses. So what you see here is 100 nanometers, 300 nanometers, 500, and 720 nanometers, and they all lie on top of the same curve. So this tells you that you have a surface-sensitive technique, because if it was bulk-sensitive, you would see those points spread out. Now, that's cool. You have a surface-sensitive technique, but is it actually spectrally sensitive? And by the time we wrote that paper, the answer was yes, but we only had 3 points, so I don't know if this is terribly convincing, but we were convinced it was. Since then, we've gone and measured some more things. And this one is particularly nice, because not just do we know the spectral sensitivity now, we also know the sort of sensitivity of it to different elements. So this right here in black is the bulk spectrum of boron. In blue, we have boron with a layer of parylene on it, which is basically just a polymer that doesn't interact with boron. And if you add, and then red is just boron by itself, so boron vacuum. And those are noticeably different, even though there's no strong interaction between boron and parylene. And that's basically convincing evidence that this is going to be a really sensitive technique, much like X-ray spectroscopy. All right. So the real question here is can you do this on liquid water? So liquid water is tricky for a variety of reasons. The big one is that you need a thin jet to do this. So you're talking about 20 nanometers the thickness of water. This can be done, I know it sounds crazy. And you have to work at half energy. There's all sorts of X-ray physics theory rules that go into this. But it should ultimately reveal a surface spectrum. So the proposals are submitted, and you never really know if your proposals are going to be accepted, but they've basically told us it's going to be accepted. So if you're interested in helping out, you should feel free to contact me, and we'll see what we can do to get you to Italy. So with that, I'm going to work on wrapping this talk up, hopefully about 5 minutes early. Yeah, that's really good. So I showed you small clusters that can be solved by VRT and how we get those structures and what they are, and how you can actually drive phase transition or drive molecular motions with very small amounts of energy. Then I pivoted and I showed how you can use something like graphene to totally change and introduce a new thermodynamically stable phase of water. And I forgot to mention this, and I'm going to mention it now. So that phase of water, if you didn't trap it, it diffuses about an order of magnitude faster than the solid and about 2 orders of magnitude slower than the liquid. So whether that's a solid or a liquid is left as an exercise to you. But it diffuses as like a wave. The whole thing will move together. Finally, I showed you how you can get the surface spectrum of water and do that by soft X-ray second harmonic generation. And I want to again tell you that I'm perfectly well aware that there are not enough details anywhere. So I will be around, and you are more than welcome to talk to me if you have any questions. All right, before I go, I need to thank a lot of people, and I apparently deleted that. So from Rich's group, Will did most of that far hour work. Royce did all that initial work on graphene, on graphite. Sumana, Raj, and Chris helped out with the boron measurements. Todd, who's now at UCSD, Keith, who's at UNLV, and David, who's at LBL, worked on those graphene water nanocapillary stuff. And I was getting paid for a lot of this from Dennis, Demos, Suchen, and Steve. And I want to point out, since I'm going to give a plug, Emiliano, Laura, Alberto, and Ricardo, who did all sorts of work getting that experiment working to do second harmonic generation. I could not have gotten here without the help of DOE and Aquaphotomics, and here's my email address, again, if you want to harass me.
Thank you, Craig, for the very, very informative talk. Questions first. Do we have questions? I have one question, maybe two.
Okay.
When you showed the spectra of ice, and I could see there's two. Yeah.
This one
before.
This
Yeah,
theirs. No,
this
so this
is
is their measurement. Yeah.
Yeah. So why do we have these two peaks? I mean, this one.
So this is the first XF peak.
Yeah.
This is the first XF peak.
Okay.
So it corresponds to the scattering of the electron losses at a certain distance as a function of the spacing between the atoms.
This is very interesting because I think Professor Hamaguchi is going to talk tomorrow, and he has found also very interesting information about the temperature of water. And we also found in infrared spectra these two, at least I think that we have these two eminent peaks of icing of the infrared spectrum. And so now maybe we can explain why. Some of you, some questions? Yes, Livia.
You showed that water trapped in graphene is the trend to become stable, thermodynamically stable.
Yeah.
Did you try to see if it is dependent or not from water, from the structure of water, using another liquid, maybe heavy water?
Yeah, so heavy water would also undergo it. They got lucky in the sense that if you had done this with, say, like methanol, you might not get that phase transition. The reason this worked was that they got a couple things sort of by happenstance to work really well. So yeah, what you saw, the phase transition is water specific, but you would see it for heavy water. It's not that different. The onset for the number of water molecules you can successfully get to become square ice at a given temperature would change where heavy water versus liquid water, but I don't know what that number would be.
Thank you.
Thank you. Other questions? Could you please explain again your video?
Yeah, okay, so this I did not...
Slowly, and yeah.
Yeah, so I knew I was being really fast on this. So this is actually a QEQ, for those of you who do molecular dynamics. So it's doing charge equivalent charge, which is actually important in getting this right. Doing what's called metadynamics. So metadynamics, I don't know if we have a lot of theorists here. Metadynamics is a way of speeding up a simulation. It doesn't change things, but it changes sort of how fast things get done, but it should not change how the actual result gets made if you do it carefully. And we did this actually carefully, but we also did it without this, but then it takes too long to show it at talk. It's like a 4-minute video. So all we're doing then is we're putting it graphene, water graphene, and we're just letting it go. And all we're trying to do is say, as you've been somewhere, we penalize that by metadynamics, and eventually it's going to find the lowest energy place. Which is why, so right here, and I didn't really explain this much, this is the free energy of the system. There is a large transition state to going over that. And so we're making that go faster by metadynamics. You should be able to do this if you wanted to spend a lot of money. You could do it in like density functional theory, but that's prohibitively expensive for this, I think. You're talking about, millions and millions of supercomputer hours, but it could be done if you're a masochist.
Thank you. Thank you very much, Greg. Thank you.
Thanks.
Thank you. Thank you very much for a wonderful presentation. Thank you. Okay, our next speaker is Yasuke Morisawa.